Hi friends, welcome to this channel. Here again, we are going to look at another lowest common ancestor of a binary tree. So this is the fourth of such problem. So in this video, we're going to do the problem following closely the definition of LCA, right? So the technique or the method will be recursion. So this is based on the data structure we are working with, because binary tree is by definition a recursive data structure. So with that said, let's quickly look at the problem statement. So basically, we are given a root of a binary tree and an array of tree nodes, objects called nodes. So we want to return the lowest common ancestor of all the nodes in nodes. And here, all the nodes will exist in the tree. This is an important assumption. And all values of the tree nodes are unique. So here, if you look at the three examples, if you look at the first one, 4, 7, then you should return 2, right? And then if you look at this 1, you just return itself for sure. And then here, 6, 7, 2, 4, so you should return 5, right? So here we're going to write a solution based on recursion. So what we are going to do is first we're going to change this node to be a set, right? So make it a set. So this making it a set is to do membership check, because for set, membership check will be very efficient with O1 operation. So now, how do we do this? Let me write a function. I'm going to call it f. I don't need to know the specific name, just see f will check, will do traversal, and going to find the lowest common ancestor. So let me first write the code, and then you're going to notice the logic. So first, if not node, so we should return node. So this if will be served also as the bounding or stopping condition. In the language of recursion, it's also called base case, right? If node in nodes. So we start from the root or from the node itself, and then once we, in this case, we should return the node. And then in this case, if node is already in the node set, then we should return the node immediately. So this actually, for example, you do this, and then also suppose you have a set, the nodes also contains 2 besides 4 and 7. Then you do up to this 2. You see, 2 is already in the set of the nodes. Then you need to immediately return this 2, because 2 will be the lowest common ancestor. So this is the one logic. Otherwise, if you do traversal and up to this node, and then you check its left subtree and the right subtree, and you found that both the two sets has intersection with the tree nodes sets, then you must return that node. This is also another logic. So these 2 points are nothing but from the definition, right? So now let's do the second one. So this is a bounding case, and this is when we do traversal, we found, we already in the node set, we should return. Otherwise, we check the left subtree and the right subtree. So f node left and f node right. So first I want to comment, this line of code is legitimate. The reason is that we have already did this check, right? If you consider the complementary, you will see node must be not null, and also node is not in the node size, right? We check this. So then what we want to do, if L and R both are not empty, right? So then what we should do, we should return the node as we mentioned, right? Otherwise, what you do, so otherwise either L or R is empty, then you just return L or R. So this will be the definition. So this function actually is a translation of the definition of LCA, right? So now what you do, you just call this function and call passing root to the argument. Then you will get the lowest common ancestor with respect to this node sets. So now let me run it. It passes the 3 test cases. Now let's look at the generic case. Yeah, it passes all the cases. So up to now, I guess we finished the coding part. Now let me make some comments. The first comment is the following. So if you work on problems related to tree or binary tree or n-ary tree or quadratic tree, so you can think of recursion, because these data structures are all recursive, because they can be defined recursively. So this is the first comment. The second comment is that when you do recursion, we know there are three parts in doing recursion. First, a base case or bounding condition. And the second one is self-call. You need to call this function itself, right? And then also, when you do this function call, the third step will be working towards the bounding case, right? Once you have these three, typically you should be able to write a valid or working recursion solution upon practice. So this is the second comment. The third comment is that we have a playlist related to for problems related to trees. You're welcome to check out those videos and do practice. With that said, I guess that's it for the current video. Thank you for watching.